Hello, Mara. Here's the work for some of the questions you had asked me about. I should point out that some of these involve things that we did not get to in class, but I'm going to go over them anyway, just to give you a general guide on how to approach something we may not have talked about in class. The first one was 11.3, number 24. And we see here that that question was to find dy dx, excuse me, wrong one. No, the right one. Find dy dx if e to the y sine x equals x plus xy. Now, the truth is, this is technically a calculus 1 question. E to the y sine x, x plus xy. E to the y sine x is equal to x plus xy. And the reason it's sort of a calculus 1 question is because when you're finding dy dx and the equation is not necessarily written as a function of x. In other words, it doesn't say y equals. You could just differentiate it across the board, but every time you see a expression or an expression containing the wrong variable like y, then the chain rule says that you follow through with the dy dx. Then you solve for dy dx, a la calculus 1. But this one specifically said to use a formula that we didn't quite get to in class. And when I assigned the homework, I forgot to say, oops, we didn't get to this yet. Number 24 says find dy dx using equation 6. But as you can see here, equation 6 says that dy dx is equal to the negative of the partial derivative of f with respect to x over the partial derivative of f with respect to y. But what is capital F that we're doing these partial derivatives on? And the answer is, if we take our equation and rewrite it so it's a function of x and y equal to 0, then whatever we have on one side is that particular function. So in order to do number 24 using equation 6, we have to manipulate the equation so it's equal to 0. Call the expression that's not equal to 0 f of x comma xy, and then we can calculate dy dx by simply doing the negative of the partial derivative with respect to x over the partial derivative with respect to y. So it's going to go something like this. All right, so first, I got my jacked up stylus here. I may have to use my finger or something. First, we have to manipulate this equation so it's equal to 0. And we could choose to put everything on the left side or everything on the right side. It doesn't really matter. I'm going to leave the e to the y sine x positive and then move everything to its side. Now I realize that I'm writing it on the right side when it was originally on the left, but just imagine on the top equation, I shove everything to the left, make say equals 0, and then just rewrite it so it says 0 equals. And then these signs of the other terms, xy and negative and xy and x would both change. So this is what we're going to call our function, capital F of x comma y. Now there's two options for this because we could have chosen to put everything on the opposite side, and therefore all of our terms would have opposite signs, but at the end it doesn't matter. Then we need to find the partial derivatives with respect to x and respect to y. Our partial derivative with respect to x is going to be the derivative of this partially with respect to x, and this, and this. All right, as far as e to the y sine of x, we're treating x like the variable, and so the y, and hence the e to the y is a constant. So this is just like a constant times sine of x, in which case its derivative would be that constant times cosine of x. And then the second term circled in pink, its derivative with respect to x is just -1. But the third one, we're treating the y like a constant. So this is like a negative constant times x, and its derivative would just be the negative of that constant. So the partial derivative there would be -y. And the partial derivative with respect to y of the three terms, starting with the first one, in the first term, e to the y sine x. The sine x is a constant times e to the y. Well, the e to the y rule is easy. Leave it alone. And the constant multiple rule says leave the constant alone. So nothing happens on the first one. Now the second expression, the minus x, is not a function of y at all. It has no y's, and so its partial derivative with respect to y is 0. We'll put a -0 there for emphasis. And then the third term, if we treat the x like a constant, the derivative of -xy is just -x. And now we got the pieces we need to assemble in this fashion to build our dy dx. We need to put negative partial x over negative partial y. Excuse me, the negative of partial x over partial y. So therefore, dy dx is the negative of the partial with respect to x, which is e to the y, cosine x minus 1 minus y, over the partial with respect to y, which is e to the y sine x minus x. Now, we could take that negative here and we could distribute it across the numerator, or we could distribute it across the denominator, or we could just leave it alone. I think leaving it alone is a perfectly acceptable move. So we'll leave that there. All right, so thanks for asking about that one, because again, it was something that I did not quite have time to get to, so I consciously made the decision not to go back to it, about finding partial derivatives using, finding derivatives implicitly, or rather finding implicit derivatives using partial differentiation. They also asked about 11.4 number 14, so I haven't looked at that one yet. 11.4 number 14, let's go to it. All right, 11.4, exercises number 14. All right. This actually has two parts, the first of which is explain why the function is differentiable at a given point. We did not go into detail on that. The only thing I wanted you to do on this one was the second part, which was define the linearization of the function. So if your concern was explaining why it's differentiable, for now, don't worry about that. Let's just find the linearization, which means we need to find the equation of the tangent plane, make it equal to 0, and I'm sorry, I'm watching the baseball game and Texas just hit a home run. Yes, to tie it. So we need to find the equation of the tangent plane, set it equal to 0, and that expression that we get is our linearization, or our linear approximation of that curve at that point. All right, so we need to find the equation of the tangent plane. All right, so f of x equals the square root of x plus e to the 4y, and we're evaluating it at the point 3, 0. 11.4, number 14. See if I remember what the function was. F of x comma y was the square root of, was it just x? I forgot. Let's see. X plus e to the 4y. Okay. Come on, share. X plus e to the 4y. And our ordered pair is 3, 0. All right, I recall that the equation in the tangent plane can be written a few different ways. One way is to write z minus z naught is equal to the partial with respect to x evaluated at 3, 0 times x minus 3 plus the partial with respect to y evaluated at 3, 0 times y minus 0. Now, of course, the minus 0 is not relevant there. I was just emphasizing where this ordered pair went. It went there and it went here. All right, so of course we need to find partial derivatives. Now, if we're going to find partial derivatives, it might be a good idea for us to write this function using an exponent instead of a square root. So let's take this ordered pair, slide it over just for a moment so it's not in the way. And let's follow up this function by rewriting it as x plus e to the 4y to the 1/2 power. This will make finding our partial derivatives a little bit easier. All right, partial derivative with respect to x of our function is going to be 1/2 times x plus e to the 4y to the negative 1/2 power, and then we have to invoke the chain rule on the inside, and we're doing partials with respect to x. The derivative of the inside with respect to x partially is just 1, because the derivative of x is 1, and e to the 4y is independent of x, so its derivative partially with respect to x is 0. Well, this is pretty easy. Now we can just write it as 1 over 2 square root of x plus e to the 4y. And when we do the partial derivative with respect to y, we're going to get practically the same thing because we still have to execute the power rule. And just so it's you can find it, because it's getting a little bit sloppy up here, the thing that I just highlighted in yellow is what we're taking the derivative of. All right, so bring down the power, leave the inside alone, lower the power by 1. And then chain rule says not sure what just happened there. Chain rule says times the derivative of the inside, but now we're doing partials with respect to y. So the x vanishes and the derivative of, oh, it was not e to the 4e to the y. It was e to the 4y. Let's fix that. Good thing I caught that before too much trouble occurred. All right, the derivative of the inside with respect to y is going to be e to the 4y times 4 because of the chain rule applied to e to the 4y. All right, so let's see what happens. Half of 4 is 2, so we'll put that on top. And then we'll get the square root of, oh, wait, the e to the 4y is up there also. That's kind of important. And then on the denominator, we'll have the square root of x plus e to the 4y. Okay, so we've got our partial derivatives, and now we just need to evaluate them at 3, 0. I didn't leave a lot of room for that here. Maybe we can do this just by observation. Let me grab all these pieces and slide them over to the left a little bit, make some room to the right. All right, let's evaluate the partial derivatives in red, because I can. Partial derivative with respect to x at 3, 0. Well, let's just talk this out so we can fit this on one page. Down here in the square root, if I put in 3 for the x and 0 for the y, I'll get 3 plus e to the 0. E to the 0 is 1. So 3 plus 1 is 4. Square root of 4 is 2. And then the other 2 times 2 is 4. So we should end up getting 1/4. And then similarly, when we do the partial derivative of f with respect to y evaluated at 3, 0. Again, when we put 3, 0 in here, 3 for the x, 0 for the y, in the denominator, under the square root, we'll get 3 plus e to the 0, which is 3 plus 1, which is 4. The square root of 4 is 2. So the 2 that we get in the denominator will cancel with the 2 in the numerator. And we're just left with e to the 4y, but y is 0. So e to the 0 is 1. So we should get 1 there. All right, so we got everything we need to build our equation except this z0. At some point, we need to actually put 3, 0 in the original function to figure out what the z0 is. But again, this is going to be pretty straightforward because under the square root, we get 3 plus e to the 0, which is 3 plus 1, which is 4, and the square root of 4 is 2. So we got all the pieces we need. The partial with respect to x is 1/4, the partial with respect to y is 1, and the function evaluated at 3, 0 is 2. So 1/4, 1, and 2. This means our equation is z minus 2 equals 1/4 x minus 1, x minus 3 plus 1 times y minus 0. Let me double check that real quick. Coefficient on the x's is 1/4, on the y's is 1. Number being subtracted from the z is 2. And our point is 3, 0. Everything looks good. So this is a perfectly acceptable answer. There are other variations of this answer, such as distributing, solving for z, et cetera, et cetera. Why don't we go ahead and, what was that I was trying to say? Why don't we go ahead and distribute and solve this for z? Because I'm thinking about the next step. Oops. How about this? All right, z minus 2 equals 1/4 x minus 3/4 plus just y. Okay, and so we get z equals 1/4 x plus y. And let's add 2 to both sides. So we'll get 2 minus 3/4, which is 5/4. And this would be our linearization. Our linear approximation. It's just saying that the surface is pretty close to this plane when we're at that particular point. All right, so that one was pretty straightforward. Okay, you also asked for 11.5, numbers 8 and 18. All right, let's go look at those. 11.5, numbers 8 and 18. Let's close this. Oops, didn't mean to close all that. 11.5, numbers 8 and 18. Okay, number 5, 11.5, 8 and 18. Okay, 8, find the chain rule, use the chain rule to find partial derivative of z with respect to s and the partial derivative with z with respect to t. And in number 8, we have z equals tangent of u over v, and then u equals 2s plus 3t, and then v is equal to 3s minus 2t. All right. Let's get this set up. 11.5, number 5, we have z equals tangent. I want to say it was u over v. I'm about to go back and check. Got to be very careful to make sure my u's and v's don't start looking the same. U over v, okay. U is 2s plus 3t, and then v is 3s minus 2t, okay. 2, 3, 3, negative 2. 2, 3, 3, negative 2. Notice I was concentrating on the coefficients. Let me double check it. U is 2s plus 3t. Yes, v is 3s minus 2t. Yes, I switched over to the question in the ebook. You didn't see me switch over though because I didn't do a screen share. Okay, so we want to find the partial of z with respect to s and the partial of z with respect to t. It might help to whip out a tree diagram. Z is a function of u and v, but both u and v are functions of s and t. So if we want to find the partial derivative of z with respect to s, we have to trace down from the z down to all the s's, so it'll be here and here, which means the partial derivative of z with respect to s, just do a partial derivative down each branch, multiply when you go down, add when you go to a different branch. On the left one, it's going to be the partial derivative of z with respect to u times the partial derivative of u with respect to s plus the partial derivative of z with respect to v times the partial derivative of u with respect to s. All of these are fairly straightforward to calculate. Well, tangent's going to be interesting. So let's, why don't we do this? Let's go ahead and write what we need to do for partial derivative of z with respect to t. And we'll switch colors just to make it a little bit easier to differentiate between the two. I'm sure there's a joke in there somewhere. Partial derivative of z with respect to t, I would have to go from the z's to the t's and just trace down my partial derivatives as we go. Down the left branch, it's going to be partial derivative of z with respect to u times partial of u with respect to t. And then down the other branch, the partial of z with respect to v times the partial of v with respect to t. So we're going to need 1, 2, 3, 4, 5, 6 different derivatives. Let's start with the partials of z with respect to u and v. Let's rewrite what z is. Tangent u over v. All right. Partial derivative of z with respect to u. Derivative of tangent is 1 over the square plus 1, so 1 over u plus v squared plus 1. And then we have to chain rule the inside. So we need to multiply times the derivative of u over v. You got another home run? Sorry. Oh, no, they're replaying the first one. Sorry about that. So we need to multiply times the derivative of u over v, partial derivative of u over v, with respect to u. Now, if you're having trouble seeing that, then take it out to the side and write partial with respect to u of u over v, and then maybe rewrite it as partial with respect to u of v to the negative 1 times u. And keep in mind that v to the negative 1 is a constant with respect to u, and so the partial derivative of this is just v to the negative 1, which is 1 over v. Now, you don't have to do all that, but if it helps, that's what you do. All right, I'll leave that down there for a moment, but it's going to get erased. Let's see if we can clean up this derivative a little bit, because it's a complex fraction, fractions inside of fractions, and that can always be cleaned up. Let's see, and I'm going to go ahead and square both sides of the fraction. So u squared over v squared plus 1, and then multiply the denominators. So the denominator of the first fraction times the denominator of the second fraction, which is just v. If we distribute the v, we get u squared if we distribute the v across the bottom, we get u squared over v plus v squared. But I still have a complex fraction, so I'm going to multiply both sides of the big fraction by v. That will clear out the little fraction in the denominator. That will give us a v on top and u squared plus v squared on the bottom. All right, so it's kind of hiding over there. We'll highlight it. There's our partial derivative of z with respect to u. And I also want to get rid of all this stuff down here so I can do the other one. We can get rid of that. Okay. Partial derivative of z with respect to v. It's going to start the same way. Derivative tangent is, oh my gosh, I feel so stupid. I did derivative of arctangent. Wait, was it arctangent? And I just overlooked it. No, it was tangent. Wow, what a catastrophe. Well, it's not too bad. I just got to undo all this. But it goes to show you, it doesn't matter how smart you are, how much you know. If you're not careful, you're going to make mistakes. That's not the derivative of tangent. It's derivative of arctangent. Derivative tangent is a little bit easier. Derivative tangent is secant squared. But I still got to do the derivative of the inside, and with respect to u, the derivative of the inside is 1 over v. So there's not a whole lot to write here. I could put 1 over v secant squared u. And I also need the partial derivative of z with respect to v. It's still going to be secant squared because that's the derivative of tangent. And the inside's still going to be the same because that's how you do the chain rule. But now I need to take the derivative, partial derivative of u over v with respect to v. So let's think about this. Partial derivative with respect to v of u over v is going to be the partial derivative with respect to v of u times v to the negative 1. U is a constant multiple, so it's going to sit there while we differentiate the v, do the power rule, and get negative u v to the negative 2, which is negative u over v squared. All right, negative u over v squared. There's not much I can do here except possibly put the negative u over v squared in front of the secant squared. Let's highlight those derivatives, shall we? Partial derivative of z with respect to u is 1 over v secant squared u. Partial derivative of z with respect to v is negative u over v squared secant squared u. But that's just these pieces. We also need the partial derivatives of u and v with respect to s and t. Those will be easy because their derivatives are linear. I'll rewrite the expressions over here so we remember what they are. Let's see. Oh, they're already up there. All right, partial of u with respect to s is just 2. Partial of u with respect to t is 3. Partial of v with respect to s is 3. And the partial of v with respect to t is negative 2. So now we have all those pieces. Now we have all the pieces that go, come on, here. So now we just got to glue everything together. Oops. I don't spend an awful lot of time highlighting these things. Okay. All right, we're ready to glue everything together. I'll be jumping around quite a bit. So, partial of z with respect to s is partial of z with respect to u, partial of u with respect to s, plus partial of z respect to t, partial of, v, partial of v respect to s, which is, okay, us and vs. Those are 2 and 3. So let's go ahead and bring those in. 2 times, and then 3 times us and vs is what I just wrote down. I need zu and zv. Zu is 1 over v secant squared u. Zv is negative u over v squared. So 1 over v secant squared u over v, and then times negative u over v squared secant squared u over v. Okay, I don't see a real clean way to write this, so we'll just mush it all together. 2 over v secant squared u over v minus 3u over v squared secant squared u over v. Now, this is not a wrong answer, but I expect this answer to be in terms of s's and t's. So we would have to place all the u's and v's with what they equal. Remember, u was 2s plus 3t. I better write this down. U is 2s plus 3t, and v is 3s minus 2t. All right. So as a function of s and t, we have 2 over v, which was 3s minus 2t, times secant squared of u, which was 2s plus 3t, over v, which was 3s minus 2t, and then minus 3u, so minus 3 times 2s plus 3t, over v squared, so 3s minus 2t squared, secant squared, u over v, which is 2s plus 3t, over 3s minus 2t. I was debating whether or not I wanted to do some factoring here, because I could factor this out of both sides. I could factor a 3s minus 2t out of both sides, and that would leave one of them in the denominator. There's all kinds of games I could play. But if I wanted my partial derivative of z with respect to s in terms of s's and t's, it would look like that. And for the sake of brevity, because that took quite a while, if we wanted to figure out the partial of z with respect to t, so in other words, if we wanted to do this one, we'd pretty much do the exact same thing. The only difference is we would use these two numbers down here for ut and vt instead of 2 and 3. All right, so I'll leave it up to you to try to work out partial of z with respect to t separately, or similarly, I should say. And then lastly, number 18. Let's take a look at that one. I may tell you not to worry about it for your test tomorrow, depending upon what type of question it is, because I know what's going to be on the test. I didn't even mean to get out of that. I'm still here. Okay. We are looking at number 18. 18. Use chain rule to find the indicated partial derivatives. We get t equals v over 2u plus v. U is pq squared of r. V is p squared of qr. And we're looking for the partial of t with respect to p, q, and r when p equals 2, q equals 1, and lil r, and r equals 4. All right, this is going to be a lot more of the same. Trying to think if there's an efficient way to pull this one off without having to redo the entire problem. And the answer is not really. We're going to have to just do it. So let's take a look at it. Okay, I'm going to do myself a favor. I'm going to take a picture of this so that I don't have to keep switching back and forth between screens. Doing number 18. All right, let's pull that up in my photos. All right, let's go back to the whiteboard. And let's take a look at 11.5, number 18. All right, we are given t equals v over 2u plus v. Try to make sure my v's and u's look different. U is equal to pq squared of r. Square root of r, not square root of 2. And v is equal to p squared of qr. I don't like that they put the r outside of the square root and after it simultaneously. I personally would have put the r in front of it with the p, so there's no ambiguity as to what's inside the square root. I guess they wanted to preserve alphabetical order for the letters, which I think is a lame reason to write it that way. Whatever. All right, so we need to find 3 partials and evaluate them at a certain point. All right, before we get into this, why don't we find all our derivatives that we can find? Oh, good grief. I'm thinking about the tree for this. We got a t, which is a function of u and v. And each of u and v are functions of p, q, and r. Actually, isn't that bad. It's just obnoxious. And if we wanted to find, let's say, partial t with respect to p, then that would be partial t with respect to u times partial u with respect to t. That would be traveling down t. Oop, that's not what I meant to do. That would be like going from t to u and then u to p. And then we also have to go tv to p. So that partial derivative would be partial derivative of t with respect to v times partial derivative of v with respect to p. Let's figure out this one, and I'll leave it up to you to do the other two similarly. All right. We'll start with the t and find its partial derivatives. T is equal to v over, what was it? It was 2u plus v. All right, let's start with the partial derivative of t with respect to u. To do that, I'm going to rewrite this. Well, I could do the quotient rule, or I could rewrite it using negative exponents. I think I'm going to choose to do that because the quotient rule here is a little bit unnecessary because the numerator is not a function of u. In other words, the numerator is constant. But I could write it as v times 2u plus v to the negative 1 power. And so the partial derivative with respect to u would be negative 1v 2u plus v to the negative 2 power, and then times partial derivative of the inside with respect to u, which would be 2. So we would end up getting negative 2v over 2u plus v squared. And let's go ahead and figure out the partial derivative of t with respect to v. And I think I'm going to use the original version of it, which I'm about to put a yellow box around. Because there's v's on both sides, I might as well just use the quotient rule. Yes, I could bypass the quotient rule by raising the numerator to the top and putting a negative 1 exponent on it. But now I'm just doing the product rule. And if I'm going to do the product rule with negative exponents, I might as well just do the quotient rule on a fraction. All right, remember, we're taking partial derivatives with respect to v. All right, low d high. So the denominator times the partial derivative of the numerator with respect to v, which is 1, minus high v times the partial derivative of the denominator with respect to v, which is also 1, and then over the square of what's below. If we distribute, well, I say distribute their ones. If we clean up the numerator, we get 2u plus v minus v, which is 2u. And then the denominator is 2u plus v squared. All right, so we have our partials with respect to t with respect to u and v. Now let's just find the partials of u with respect to p and v with respect to p. Those are actually pretty easy because they don't have the square roots. If we did the square root one, we would raise it to a 1/2 power, do the power rule, maybe put it back into a square root. But here the partial derivatives with respect of u with respect to p and of v with respect to p are going to be fairly easy. In fact, I'll just do them right here. Partial derivative of u with respect to p is q squared of r, and the partial derivative of v with respect to p is square root of q times r. I don't know why when I'm drawing my r's, I'm trying to draw 2's. I haven't figured that out, but I've done it quite a bit. Okay, so here is our partial derivatives of u and v with respect to p. And here are our partial derivatives of t with respect to u and v. So now I just got to glue them all together to find the partial derivative of t with respect to p. Okay. So partial derivative of t with respect to p is going to be the partial derivative of t with respect to u times the partial derivative of u with respect to p plus the partial derivative of t with respect to v times the partial derivative of v with respect to p. All right, partial derivative of t with respect to u is negative 2v over the square of the denominator. Negative 2v over the square of the denominator, which was 2u plus v. And the partial derivative of u with respect to p was q squared of r. Q squared of r plus partial derivative of t with respect to v, which was 2u over the square of the denominator. And then the partial derivative of v with respect to p was square root of q times r. And can we possibly make this any better? Well, I guess we could merge all the fractions together into one giant fraction because they have the same denominator. I don't know if there's a benefit to that or not, but we'll call it 2u plus v squared in the denominator. And in the numerator, our first numerator will be 2q squared of r v. And our second numerator will be 2 square root of Q R U. And then we can replace V and U with what they equal. V was equal to P squared of QR. So V had the Q square rooted and U had the R square rooted. Okay. Negative 2Q squared R. I forgot which one had which. U has the R square rooted. V has the Q square rooted. So V is going to be P squared of QR plus 2 square root of QR. And U has the square root of P, no, square root of R. U has the square root of R. So square root of R, PQ squared of R. PQ squared of R. And in the denominator, we have 2U, so 2 PQ squared of R. Plus V, and V was P squared of QR. And all that's being squared. Can this mess possibly be cleaned up? Actually, it doesn't matter. That was my phone unplugging. The reason it doesn't matter is because I didn't write down all of the question. Yes, I could simplify it. In fact, I could even take advantage of the fact that on number 18, we have P is 2, Q is 1, and R is 4. I could have taken advantage of that a lot sooner. 214 is in Dallas area code. I could have figured out the values of these partial derivatives and these partial derivatives at the values of P, Q, and R, except these weren't in terms of P and Q yet. But I could have figured out what U equals and what V equals, and then okay, so there's a lot of ways I could have plugged in the numbers a lot sooner, but let's go ahead and plug them in right now. Oh boy, 214 is what it is. I'm not worried about that. I'm worried about putting them in, remembering all this as I write it to the next page. Well, I can just do this. Let's get rid of all this and this. And let's just move this up. Since I'm just worried about getting to the solution right now and not preserving all the work, I'm okay with this. Now, if I'm going to make myself some room, I might as well try to clean this up a little bit. The theoretical guy in me wants to clean this up, so bear with me as I do this. But to conclude this problem, we just have to put in 2, 1, and 4 for P, Q, and R. Let's start by cleaning up this guy. Let's see what we get. All right, we get negative 2. We only have a single P. We have a Q and a square root of Q, so that's Q to the 3 halves. And the same thing with the R. And then on the other one, let's move my face out of the way. On the other one, we get a 2. We have a, oh my gosh, I just saw something. We have a Q. Are you serious? To the 3 halves and an R to the 3 halves. Are you serious? These things cancel. It doesn't matter what's in the denominator now. This is equal to 0 unless I did something totally wrong. And I'll be honest, I've had a long day and I'm a little tired right now, so I very well could have done something wrong. But the values of P, Q, and R don't matter anymore because it appears that the numerator is 0 because both halves of the addition problem are opposites. So, interesting. Kind of curious if that's correct. Well, this has been a long video, and I assure you that of the stuff that we've done so far, and I can backtrack, this one is far worse than anything that you will see. Oh, that is another home one. Far worse than what you'll see in your test. This one is pushing the boundaries of what I would put on your test. This one, however, is a very good representation of something I would put on your test. And then this one was I like the partial derivatives, but we didn't talk about how to use them to find a derivative implicitly. So you can infer from that whatever you would like. Okay, hopefully this has been of some help to you. I know it was a long video. I don't know how long it is. I'll find out when I upload it.